No, cyclotron. So if you look at the many nuclear science, especially in the medical fields, no, we need, there's a necessity of what, like a high speed moving charge particle. Okay, then already we did this in electrostatics, no? If a charge particle accelerates through a potential difference, then it will acquire a kinetic energy, that is mv square by 2. And what is v equal to? 2qv by m. Look at v. What is v? V is a potential. Charge of electron, mass of electron, check it in to acquire, to have that very high speed, what happens, you have to apply a very large potential difference. To have that large potential difference, lot of power is needed, electrical power, and the cost will increase here. And we do have some limit. What is the maximum possible energy we'll get it? The kinetic energy what we get is 200 kilo electron volt. More than this, not possible. Why I'm writing 200 kilo? What is the maximum possible voltage we can have? You look at outside transformers, it'll be written, no, there, like a 200 kilovolt, 1 lakh. Now little bit technology improved. Okay, we are going up to say like a 1 lakh volt. Even that you put it 1 lakh, no, still the speed will be very small. But practically what we needed for applications, we need kinetic energy of order 100 mega electron volt. To have 100 mega electron volt, what's be the potential difference? 10 to power of 8 volt. Such a large potential difference, though you generate, it will be very problematic. Okay, of course in the transformer, okay, there, step up, step down transformer. But to just accelerate a charge particle, we cannot generate a potential difference of 10 to power of 8 volt. You see, mega means 10 to power of 6. So such a large potential difference is a big headache. So how to overcome that? So for that purpose, what happened? We have brought a cyclone. So what are the first major advantages of a cyclotron? A charge particle with a large kinetic energy can be generated. Already we have electrostatics, we have studied, but there, what is the maximum limit now? 200 kilo electron volt. But for our applications, we need of order several hundred mega electron volts. Okay, getting this one. So where do we use accelerating charge particle? I think in most of the nuclear reactions, proton should bombard some nuclei for the reaction to occur, or most of the medical devices, they got a charge particle should accelerate. No, I think you might have come across many resonance properties in that one. So we need a accelerating charge particle. So to operate medical devices and the nuclear devices. And for that purpose, the cyclotron is a device. Let me introduce the diagrams. It's again drawing, it will be. And if you look at the mains, no, that they're asking plenty of questions related to this. Huh? You should be very careful about the type of exam, mains exam. Charge particle moving in a magnetic field. Then what all the Lorentz force problems we did know, this is very important. The preparation for mains should be, especially not, not weekend. You look at the final exam, no, what all problems we did, motion of charge particle in magnetic electric field, no, how much that are important, equal weightage for this one small topic. So when you're going for mains exam, JEE mains, what to revise? Motion of charge particle, first cyclotron, then next are all other things what we discussed. The preparation for mains is little bit, it should be a well calculated one, not like the thorough like in advance. You should be smart enough. Smart preparation is what you have to do, rather than like a preparation what hardcore preparation what we do, no. So than that, it should be smart preparation. Yeah, come for this. Now there is a alternating current, source of alternating current. So these are called as D's. So these are called as D's, that one. D's means you look at the how it's like a symbol D, no? And I'll shade it. You can, how do this, the old structure, it appears like a symbol D, capital D. So therefore, they are called as D's, D double E S. Now, to make atom bombs, all know you need all these nuclear reactors. How sophisticated you are having these equipments, what happen? The more powerful will be the nuclear reactor. Even nuclear reactor. So many of the scanning equipments, they need all this one. Come for this. So look at the symbol green color one. I'm shading it. So how do it appears like a capital D? So therefore they're called as a D's. They're called as a D's. What is our main purpose? I should get a high speed moving charge particle. Okay, now come for this. Once again, I'll go back to the theoretical ideas. QV equal to, this is a kinetic energy. So what is our requirement? Our requirement is something 2 mega electron volt. So this E and this E will get cancelled. Let's see that. EV equal to 200 mega electron volt. So what is the required potential difference? One E get cancelled. So this will be 2 into 10 to the power of 8 volt. Let's go for E equal to VD. So V equal to E into D. Let's take the electric field of say like a 1000 volt per meter. Then what should be the distance? Or 2000, I'll write it. 2000 volt per meter. Then what should be the distance D? You should take it here. 10 to the power of 5, no? I think this will really help you. Like why we should go for cyclone. What is the distance D? In place of distance D, what we have? 10 to the power of 5 meter. What do you mean by 10 to the power of 5 meter? Convert into kilometer. So what is the distance D required now? It will come to D is equal to 10 to the power of 5 meter. 100 kilometer. So what should be your equipment? I should have an equipment, electrostatic equipment, what happen, whose electric field strength should generate 2000 volt per meter, and till where the field should extend till 100 kilometer. Practically possible. This is absurd, no? Totally that one. So what is the biggest headache will come? The D will be a troublesome. It should be as small as possible. So can we allot for a nuclear reactor 100 kilometer some length of the pipe or some other thing? This much of space can we allot? Or just for scanning equipment, can you give this much of space, 100 kilometer? It's totally no, that one. So to overcome this is what the cyclotron. Are you getting no? The rest of everything, so we'll come into this one. Let's get into charge particle. Now, charge particle, I'm going to release here. I'm going to release a charge particle. So what that electric field will do? Okay, I'll start from here. I'll release charge particle. The electrostatic force will accelerate it and it enters magnetic field. And we know work done by magnetic field should be zero. So what it does, it just completes semicircular path here. Again, it enters electric field. By the time it enters, no, again, I'll change the direction of field. So means when the charge particle space not sufficient. I'll come here. There's a gap, so we'll start with the midpoint. So here the charge particle are released from rest. And to this, what will happen to this particular, I'll apply electric field, which will be of this particular thing. Now in this gap, there'll be electric field. So now the electric field will be, how it will be directed? Let it be in the direction. So this charge particle experiences a force. So because of this electric field now, it will accelerate. Then it will enter with a velocity, say v1. Now b bar, let it be into the plane. How do it will bend? The magnetic force will act and it is going to revolve in a circular path. So here there is no magnetic field. No magnetic field. No. It's a gap. In this gap, no magnetic field. There is a magnetic field everywhere here. Electric field exists only in the gap. And now again it enters here. By the time it enters here, I'll change the direction. You can see positive and negative peak. Are you able to notice here? Positive peak, and here the field will be. What are that blue color and green color? The direction of field in the gap will change. So now by the time it enters here, the field direction, I'm going to change it. I'll give that corresponding colors. Green it is. Now by the time it enters here, again the direction of field I'm going to change. So what will happen to charge particle? It's going to enter with a speed v1. By the time it passes here, how much of speed it will acquire? v2. It will get accelerated, no? Then because of speed, we know R equal to what? mv by qb. If speed increases, m and qb are constant because there is no any magnetic field in this region, only electric field, so it will accelerate it. Then as v increases, R should increase, so it's going to describe now a path of increasing radius. So where do you should come? You should come here. And it's a constant speed. Here speed will be v2. So when it arrives here, it will have speed v2. And now look at the electric field. It will change direction. Again, it will come like this, E. It will accelerate the charge particle. It will become v3. Again, v3 greater than v2. So it's going to describe so here and everywhere speed, how much it will be in this magnetic field will be v3. So when it arrives here, this is v3, it will get accelerated, will become v4. So now what is the direction of field? Will be E. So like this, what happens? The charge particle, I am going to make it accelerate. Are you getting now the idea? So whenever it, we can change it. We can change it. We can change it. There's no problem. We can change it. So what happened to charge particle? In this gap, it will get accelerated. In this region, it will move with a constant speed. I'm showing that V4 also, so that will be easy for you. There is no increase in speed, only direction changes. So what magnetic field does? It will change direction. So what is the role of B bar? To change direction. What is the role of E bar? Increases speed. Finish short. There's a core idea. Where the charge particle speed will increase in the gap. I'll take it out this. So speed of charge particle, speed of charge particle increases in the gap. So and in the magnetic field, what happens? It's going to describe a uniform speed motion. That one in the gap, it's going to get accelerated. And now, what is the maximum? To get a very high 200 mega node? What is the maximum possible radius of this? Will be around 17 meter. I think this is not something 17 meter space can we allot for any nuclear reactor? 17 meter, 17, not kilometer, just 17 meter. By the time charge particle from rest when you release in the gap, by the time when the radius of circular path is discovered by charge particle is around 17 meter around, then what is going to acquire the high speed of order of few hundred mega electron volts. I think what happened, the size now, the size of equipment has brought down. No? There's the overall core principle. So what is the requirement? What we should do here? Now we know what is the time taken to move from one to, okay, this, I'll give points A and B. What is the time taken to move from A to B? This is A to B. What is the time taken to move from C to D? What is the time taken to move from E to F? What is the time taken to move from F to G? Anybody? Let's try to search some ideas there. TAB, time taken. Shall I say, is it equal? How come, sir, different paths, same time period? So time period depends on what? 2 pi m QB, no? It doesn't depend even the radius also. So TAB is equal to TCD is equal to TEF is equal to TFG is equal to how much? Pi m by QB, no? Half of the time period of revolution, it is independent of R and also what? Independent of the velocity, the speed of the particle. Is it okay? I'm just giving enough information, just analyze here. Half of the time period of revolution. So what time it takes to move from A to B, same time it takes to move from C to D. This one. So now tell me like this particular signal, what I'm applying. This is what a generator. Electric field generator. So what should be the requirement of that generator? In books, story is available. So definitely when it comes to exam, no, so they will ask you all about the in-depth, the electric field or the potential difference, the cell what you're going to connect, no, should generate electric field of this nature. The potential difference across the gap should be of this kind. This is t equal to 0. So what should be this time? What should be this time? Pi m by QB. What should be this time? Pi m by QB. This is what I'll just shade one so that it will be easy for you. Shall I apply a sine wave or this square waveform? This is called like a square waveform. So it should be a square waveform. It should be a square waveform, that one. So what should be the time period of this? Should be called time period of revolution of the charge particle. Okay, good insert. So there shall I call this is the T now. I think all of you know function, periodicity of a function. So this is this part of the graph will repeat again and again, no? If you see this, what part of graph will repeat again and again? This part of the graph will repeat again and again. So shall I call that periodicity? So time period is what? What should be the time period of signal? Time period of signal should be equal to the time period of revolution of charge particle inside that D. So therefore, this is the one conditional put it. So we know T is equal to 2 pi m by QB and F is equal to 1 by T. So what should be the frequency of the electric field generator? That should be equal to the frequency of the charge particle revolving in this particular cyclotron. So then only resonance occur. Then we'll get a maximum speed. What do you mean by resonance? By the time exactly the charge particle completes off revolution, what should happen to the E bar? E bar should change direction. You can see here. The E bar should change direction. It should get accelerated. So this the mechanism is what? The resonance should occur, that one. So this should be the frequency of revolution. So what is the frequency of the applied signal? This should be equal to QB by 2 pi m. Frequency of cyclotron it is called as. When the frequency of applied signal becomes equal to frequency of revolving particle, then it's said to be in resonance. Okay, this overall mechanism. Now let's come for the structure will be like this here. This is the who will produce that magnetic field? This is the electromagnet, north pole, south pole. So this is like a magnet. You can see here it's telling the uniform magnetic field. So what is the role of electromagnets? They'll produce that uniform magnetic field. Then here is what the charge particle is going to, and what is the condition for that electromagnet? It should not produce any field in the gap. You see this one, where the field should exist only in this region, green color. In the red color, there should be only electric field. You know, in the gap, no, in this gap, there should be only an electrostatic field must be there. And who will produce that electrostatic field? An AC generator. External beam, you can see that one. No, come for this. This electromagnet open should see that it should produce field only in this semicircular regions. It should not produce any field in the gap. In that way, it should be designed. Then next, what is the gap? In the gap, what happened? Which field will exist? Only electric field. What is the duty of that? It should accelerate a charge particle. Now you can see that I'll leave the charge particle here. The field will accelerate it. So it's going to revolve in a circular path of increasing radius. And we know Q, M, B are constant. As R increases, V will increase. So when the charge particle emerges out, it will emerge with a high speed of order of few mega electron volt. And with that kinetic energy, it will go and strike some nuclei, some target. It's called like a target you can see here. So it will be channelized. Again, once this field comes, suppose this target is far away, with the help of magnetic field open, I will make it to move in one specific direction. With the help of electrostatic field, all that one. No. Nothing like that. We can't beat. Okay, like this. So that particular, it will go and strike the target, the particular nuclei where you want to bombard. No, so there you can use this particle. So what is the diameter? What is the radius of this cyclotron needed? Around 17 meters. That is enough to generate a charge particle of order mega electron, a few hundred mega electron. Now a few questions like why we can't use electron here? There's one strict condition he has put. Why we can't use an electron? There's one condition he has put it. We can't use electron for this point. So any reason for that? It cannot, so like a first limitations will put it and all. So can it accelerate neutral particle? No. Neutrons cannot be accelerated by cyclotron. Correct statement, no? So what limitations will put it? Limitations or first thing, neutral particle cannot be accelerated. Next again, so if you take the lighter particles cannot be accelerated. Lighter particles example, the lighter particle examples are like electrons. Lighter particles are electrons or that one. So any reason for that? Because of relativistic mass, because as the speed increases, what will happen to the mass of that one? So it will become, you have to go for, instead of this effective mass, you have to go 1 minus v square by c square. So no longer you can't just take rest mass of the electron, you have to take the relativistic mass here. This is the rest mass. This will be relativistic mass. So as if you bring the electron into picture for calculation purpose, you have to introduce this one. So no longer I think your expression for R is not simple mv by qb. You look at that one. In place of v again, it will be this. So the path will not be perfect circle. So a lot of calculations, complications will come into the design of that cyclotron. This is the one thing. So because electrons are lighter particle at higher speed, as the speed proportionally increases, no, so definitely the relativistic mass will come into the picture here. So therefore, the lighter particles are not used. One more limitation is like as you go for lighter particle, you need high frequency. Any reason for that? I think we have generated formula, no? Where is the formula? Come for this. As m decreases, lighter particle, what happened to frequency? Very high frequency. Very high frequency means we have to generate a signal, electric signal, which will have high frequency. It's a very big problem. So what is another condition I have to put it? Third one, for lighter particle, high frequency alternating electrical signal has to be practically not possible. These are some in books. What happened? They didn't stress all this. These are some limitations what we have for the cyclotron. Now, what is the energy of the particle emerging out? What will be the expression for kinetic energy of the particle? mv square by 2. So shall we bring expression for that from here? So it depends upon the radius of the D's, no, finally, because the radius of this will finally determine. So when it is emerging out, you can see it is emerging out. So this will determine the radius, no. Got this one? So this radius, what you can write it like mv square, where r equal to mv by qb. And the v again depends on what? The exciting potential. So how to the kinetic energy of that particle, it depends upon the radius of the beam. So v you write it, no, m by 2. V you can write it as qbr by m whole square. So therefore k is qbm, they are constant to check it all. K equal to, this will be b square q square b square by 2m r square. So greater the radius of the D's, more the kinetic energy. So therefore, the cyclotron with more radius as the charge particle will circle more there and it's going to acquire more speed. So I'm just indicating the diagram, this one, this R and this kinetic energy, they are related according to this equation. No. Again, see, like a relativistic mass comes, the equations will change. Okay, things are a little bit different. So that we'll call it a synchrotron, synchron. Very complicated operations are there. So only a basic idea of this one. It's not there for advanced, but they may ask you as a general passage. You have to be very careful in advance. Okay, Henny, I'll stop it here only.